Watch a straight line bend term by term until it becomes a perfect sine wave. A polynomial just powers of x pretending to be a curve it has no business matching. How is that even possible? This is the magic of Taylor series. Add the right powers of x and you can rebuild almost any smooth function, but there's an edge, a radius beyond which the magic suddenly breaks. Let's see it, then solve two real AP problems. This is Full Marks. Today, Taylor and Maclaurin series building curves out of powers and finding exactly where that approximation stops working. The idea: near a point, copy a function with a polynomial, start by matching its value, then match its slope, then its curvature, then the next derivative and the next. Each new term you add fixes one more derivative so the polynomial hugs the curve more tightly. Centered at 0, that's the Maclaurin series. F of x equals the sum of f to the n at 0 over n factorial times x to the n. The nth coefficient is just the nth derivative at 0 divided by n factorial, tuned so the polynomial's nth derivative matches the function's. Watch sine get built. The first term is just x, a straight line. It matches near 0, then flies off. Add minus x cubed over 3 factorial and it bends back into a wave. Add plus x to the 5th over 5 factorial and it hugs the curve even further out. Keep adding terms and the partial sums wrap tighter and tighter around the sine curve, matching it over a wider and wider stretch. For sine, the series eventually agrees with the function everywhere. But not every function is so generous. For many, the approximation only works within a certain distance of the center, the radius of convergence. Push x past that wall and the partial sums don't settle down, they blow up to infinity. So how do you find that radius? The ratio test. Take the absolute value of the ratio of consecutive terms, let n go to infinity, and require that limit to be less than 1. Solving that inequality for x gives the open interval where the series converges. The ratio test nails the inside of the interval, but it's silent at the two endpoints. There the limit equals exactly 1, which is inconclusive. So you test each endpoint separately by hand. That finally gives you the exact interval of convergence. Exercise 1, a real AP question. Which is true about the sum of -1 to the n over 1 plus root n? Is it absolutely convergent, conditionally convergent, convergent but neither, or divergent? It alternates and 1 over 1 plus root n decreases to 0, so by the alternating series test it converges. But take absolute values. 1 over 1 plus root n behaves like 1 over root n, a p-series with p 1/2 which diverges. So it converges but not absolutely. That's conditional convergence, answer B. Exercise 2, a real AP free response. The Maclaurin series for f is the sum from n equals 2 of natural log n over 3 to the n times n cubed, all times x to the n. Use the ratio test to find the interval of convergence. Form the ratio of the n plus 1 term to the n term. The log and the n cubed parts each approach 1, the 3 to the n leaves behind a factor of 1/3, and you're left with the absolute value of x over 3. Set that less than 1, the absolute value of x is less than 3. The radius is 3. Now check the endpoints. At x equals 3 and x equals -3, the series becomes plus or minus the sum of log n over n cubed, and that converges, because n cubed completely overwhelms log and both endpoints are included, so the interval of convergence is the closed interval from -3 to 3. Recap: a Taylor series rebuilds a function from its derivatives. Coefficient n is the nth derivative over n factorial. The partial sums close in on the function but only inside the radius of convergence. Find that radius with the ratio test, then test the two endpoints by hand for the full interval. We can now build and bound infinite series, but on the exam the real challenge is choosing which convergence test to use and when. Next time, one flowchart that picks the right test every single time. That's next on Full Marks.